Hi everybody. Today you can see the title up at the top of the screen. We're going to work our way through some exponential growth and decay problems. I'm going to argue to you that a large majority of what we cover today should be review from previous years. However, we are going to address maybe the way that we could get into some extra problems, that is, some conditions that had to exist in the past don't have to exist anymore because we have more tools with us. But also we're going to finish off today with just a little bit of a stretch into a new concept. So what you see on the page is our first example that I want to go through, and I've just put on this big relationship on the screen. Now, in terms of your A, your P, your G, your T, your P, it doesn't really matter what letters you use as placeholders in those spots. I've just come over time to use those letters to represent certain ideas. So let's break down what each one of those components are, if you want to think of it that way. Now, I've listed out quick little definitions for what each of them are, or labels for what each of them are. Hopefully that sort of relationship is something that you're familiar with from last year. The idea that if we're going to talk about exponential growth, then it has to fit into a relationship where each component relates to itself or to the others in a certain way. So we see this relationship, and you might call it like a formula, but it's a relationship that would say like A equals P times G to the exponent T over P. So let's just break down each component for a second. That A on the left side, that is our accumulated amount. Now, I always kind of get worried a little bit every time we use accumulated, because a lot of times people tend to think of accumulated as like it's building up and up and up. And so they put this idea in their head that your A value has to be big or bigger than something else. And really what we're talking about when we say your accumulated amount is that's the amount that gets changed to. So it's kind of the result of something. Okay, you take a look at your big P, the P in blue, that is our initial population, so that's our starting amount. You look at the G, and the G is our growth. Now, the easiest way to come up with what your G represents is if you can sort through the problem and figure out how does the population change. That is, if you can answer that question, then you know your G value. Now we look up into the exponent. I think the top of the exponent should make sense. That is our T, and that's where we talk about elapsed time. When we get into some alternate problems where it's not really time that we're dealing with, then maybe what you're looking at is like the number of changes that occur. And then on the bottom, you see like another P. Now, I understand that if this is a formula, it's really bad to use two of the same variable. I could be a little smart alecky and say like, but the blue P is a big P and the orange P is a little p, but I know that's hard to tell with P's. Really what that little p is, it represents the period. And if you're ever trying to figure out what the period is, then if you can answer the question, how long does it take to G, then you know what that value is. Now, the question, how long does it take to G, sounds a little weird. But that relates to the G that is the base of that power, that purple G. So if you can figure out how long it takes to do that population change, then we can come up with our period. So there is a relationship that is going to exist in every exponential growth and decay problem that you will encounter. So if you like that formula per se, then let's use it all the time. The next issue becomes when we read an application problem, when we get some information to a problem, how do we know if it represents an exponential growth problem? And so I'm hoping that when we see that exponential growth aspect, then really what we're trying to hammer home is the idea that something is changing based on an exponent. Now, when we see an exponent, really what we're talking about then is repeated multiplication. Now, I don't want anybody to think that I wrote that in orange and therefore that somehow relates to the period. Not at all. What we're just talking about when we say repeated multiplication is something has to be changing through a repeated action of multiply. Now, maybe that means it's a percentage change. We're going to jump into some problems today, but I want to make sure that we always start from the beginning. We don't assume exponential growth, but instead we determine exponential growth. So we're going to start out with that first problem that's listed on your page. Now, I'm just going to shrink down that problem a little bit, just so we can have a little more space to be able to include a solution. Let's say that you were starting off this problem. You read the problem. Now we have to try to determine what type of relationship this is. I want you to pause it real quick and give that problem a read. Okay, we're back. So I can tell when I read that problem that this is an exponential growth problem because there's my word of doubles. If something is doubling, then I multiply it by 2, then I multiply it by 2, then I multiply it by 2, and so on and so on. That's what represents my repeated multiplication. And as soon as I determine that it's exponential growth, then I know that this relationship must be true. Now, if that relationship is completely new to you, then I might suggest writing that down as your first line of your solution every time. Drill it in. But if it's something that you're used to, like I never have to see that as part of your solution. Okay, what we can do is we can now take the information we have in the problem and try to fit it in to each one of those components. I think maybe the first thing we might be able to come up with is my G. Notice, my G, my growth, is how does the population change? And we already addressed that in determining that this was exponential growth. It doubles. Therefore, my G is 2. Okay. I continue to read the problem, and it tells me that the bacteria in a culture doubles every hour. What that every hour tells me then is my period. That I double every hour, which means if I go to answer the question for my period, how long does it take to G, how long does it take to double, then I can put down over 1 hour. Now, obviously we don't have to write down over 1 in a fraction, but let's just leave that there for right now. I keep reading my problem. The initial population of a culture is 36. So I know that my big P is 36. The question says, determine the number of bacteria, which means I'm trying to find A. After 570 minutes, 570 minutes is my elapsed time, and maybe I plug that in. Now, I just want us to see that that would be the location of where we could sub in all of that information into that relationship. We made an error, but I just want to draw to our attention that that's the location of everything. Okay, I want to come back to one key feature in this problem. Okay, and all this is just a key feature. And it's something that we didn't state earlier on, but it's something that should be relatively logical. That up in my exponent, I have 2 components, elapsed time and period. And if I'm going to talk about those 2 components being related, they're within the fraction, then I have to make sure that they're in the same units. So I just want you to notice, look up into the exponent and maybe we can see our mistake. The 570 was in minutes, but my period I put in hours. So we have to just make sure that those are in the same units. It never matters what units we're talking about. So my guess would be that most of us would find it easier to take that 1 and now if it takes 1 hour to double, then that 1 hour would be 60 minutes, and we're good. So by just making that change and ensuring that our exponent is in the same units, now we have our relationship. You're good to go ahead and push buttons on this. You're fine to go through. What I would ask you to do in your notes, though, is go ahead and give me your solution to that to 1 decimal place. So I actually want you to push some buttons on this so that we can make sure that we're good with our keying sequence on our calculator. So I would suggest just punching it in according to bed mass. Take your 2, put it to the exponent of 570 divided by 60. Now multiply that by 36. And if I was to write it out to 1 decimal place, then we should, that's a really 6, get something like this. And there we go. Now, I need to talk a little bit about rounding. So I just want to shrink this down a little bit more just to give us a little more space. That hopefully we can look at it and we can say, okay, either I'm going to have a bacteria or I'm not going to have a bacteria, but there is no way that I'm going to have 0.8 of a bacteria. And so we can start to see solving problems like this pertaining to people, to animals, to certain things, populations, where maybe I have some inherent rounding rules. Like we can see some instances where I can't have a part of something, I must always have a whole. And so we have to look at this case and say, okay, well, how are we going to round that bacteria? Now, I hope that everybody would have rounded that to 26,066. Okay, I'm going to bet and say we had a bunch of people who didn't. And I'm going to bet and say that 0.8 that I circled, I would have some people that go, but wait a second, doesn't that bump that up to the 67th bacteria? And I need us to think about how that population is growing. I want you to notice that that population is doubling over time. And so if it's doubling, then my bacteria is increasing in its population. So I just want you to imagine like that last instance of time, we would have had 26,066 bacteria, and then a little bit more time went by. That's what allowed us to get up to the 0.8 of a bacteria. Well, if we acknowledge that you can't have a part of a bacteria, then the amount of time that has happened has not been enough time to create that extra bacteria. So even though like our rounding rules say that 0.5 and above means we round up, practically that 67th bacteria could never be created because the 0.8 of a bacteria could never be created. And so we're forced to round down. Your final answer in this case is 26,066 bacteria. Now, I also want to make sure that nobody put an idea in their mind that says, oh, so I guess we always have to round down when we do these problems. I want to be really clear that it depends on what is happening to the population. Let me take an alternate case. Let's imagining that we had a decay problem. That say over time our population was like it was losing 10% of its population every hour. Well, if my population was going down and I finished with 26,666.8 of a bacteria, I can't have 0.8 of a bacteria, so I have to figure out how I'm going to round in this case. If I finished with the green, then that must have meant that at some point I had 26,067 bacteria, and then I lost 0.2 of a bacteria, and that's how I got to the 0.8. But for the same reasoning we just spoke above, if I can't lose 0.2 of a bacteria, then I couldn't ever get down to 66. And so when I round off, I would round off to the 67. So I just want you to notice that our rounding rules have to be opposite what's happening to the population. If my population is increasing, then I can't increase a portion of a unit. I have to round down. But if my population was decreasing, I can't lose a portion of a unit. Therefore, I have to round up. Okay, we're going to see that in our practice as we work through our problems. But just keep that in mind for any times that we have some inherent rounding rules. Okay, we spent an awful lot of time on a pretty straightforward question, but I think we knocked out a lot of information in that problem. Now it's time to just kind of see different exponential growth and decay applications that we're going to come across. So let's jump into your next one. What you see on the screen, we've got a word problem. I want you to pause the video, give it a read. Okay, we're back. So you gave that a read, and as we start to read that problem, we might not be able to recognize whether that's an exponential growth or decay problem. So you're reading this at the end of the year, you got all these problems all jumbled up. How can you tell what type of problem it is? If everybody can just underline or highlight half-life. Half-life should have been a concept that you've come across in your grade 11 course. It might be a concept that you've come across in other courses, science course, for instance. When you take a look at half-life, what half-life describes is how long it takes to get to half its life. So if I started with a population of happy face, then half-life in this case is 8 years. What that tells me then is it takes 8 years to get to half of what I started with. Then it would take another 8 years to get to half of what I had there. And then another 8 years, and so on and so on. So maybe you can see that by me dividing by 2, dividing by 2, dividing by 2, well, repeatedly dividing by the same number is the same as multiplying. Dividing by 2 over and over again is the same as multiplying by 1/2. Multiplying by another half. Multiplying by another half, and so on and so on. Anytime we see that half-life, then half-life is an application of exponential growth. So as soon as we recognize that, then we know that our relationship can be represented by that. And now let's just kind of sub in the particulars to make sure that we're good with it. Okay, you take a look at what I just drew out in green and red, and hopefully you can see your G. What is happening to our population? It is getting cut in half repeatedly. So my G is 1/2. It told me in the question that it takes 8 years. That's my half-life, 8 years. That means that my period, how long does it take to get to half? There's my 8. The question then says an original sample has a mass of 128. And at the end of some amount of time, I've got 2 milligrams left. The question asks us, what is the elapsed time? That's what I need to solve for. So I'm going to ask, since we kind of translated that problem together, I want to see if we can solve that problem mechanically on our own. So I want you to pause the video right now and you try to solve that equation. Okay, we're back. So this is where we start to say, like, now what we have to do is we just assume we have equations in front of us. They're all jumbled up. We can sort our way through it. So first question you always ask yourself is, where's the variable? It is up in the exponent. And so if my variable's up in the exponent, I got to get it out somehow. That means I need a power equal to a power base the same. So first thing I can do is I can eliminate that 128. It's attached by multiply, so let's get it out of there and let's divide it out. This is where sometimes, if you're a bit of a button pusher, it can get you into trouble. That if you go and calculate 2 divided by 128, then you're going to get like a pretty ugly decimal. And it might be difficult for us to try to interpret that big ugly decimal. However, if we leave that as a fraction and then just take a look and see, can we reduce that fraction, we should be able to see that we can divide a 2 out of top and bottom. And if I get to that line, we should be good. Best way to solve an exponential equation is to get a power equal to a power base the same, and I can now write 1/64th as a power base 1/2, because I recognize that 64 is 2 to the 6th. Well, now that I have my power equal to a power base the same, I can then say, therefore, my exponents are equal, and now I can isolate for t, and I can multiply out my 8. You get down to that point, the only thing that I need you to do is just put on your units. And we discussed in the last problem that our exponent has to always be in the same units. So as soon as we plugged an 8 in for our period, then we defined our exponent, if we look up in the question, in years, which then means that that 48 must also represent years. And there you go. Okay, expectation level for the course. You need to know that if you can solve an exponential equation by writing as a power equal to a power base the same, then you are expected to do so. So I would need to see that purple solution. Anybody who was up with my little happy face expression that said, hey, I started with 128, cut it in half, cut it in half, cut it in half, and then just kept going to see like how many times you cut it in half gets you all the way down to 2, you would get nothing for that when we evaluate that. We need to see your understanding of, can you apply that to that relationship? And I want to see your algebra, because this is a direct application of your algebra theory. Okay, hopefully that brings back a little bit of half-life. We're comfortable to use it. Let's jump into the next problem. Okay, you can see the problem on the screen. I want you to pause it. Come back when you're done reading it. Okay, so we've given the problem a read. Now what I want you to do is I want you to try to start that one off on your own. So you give that one a go. Pause it now. Okay, we're back. So I'm hoping first off that we can recognize that this is exponential growth, because we're talking about losing a percentage. How long does it take to lose this? We're talking about half-life. That's something to get to half, to get to half, to get to half, and so on. We have exponential growth. So I know that I can start off my problem with our relationship. And make sure that looks like a G. Now, all I'm going to do is I'm going to erase the information in that problem. Okay. I'm going to bet and say that our attempt probably, because half-life was there, meant that most people took your G and replaced it with 1/2. Let's make sure that we have brackets around that 1/2 so that we make sure that the exponent applies to all parts of the base. And if that was the case, then we probably plugged in an 18 for our P. How long does it take to get to half? 18 hours. Here's where we maybe got a little bit of a jam. The question says, how long does it take? So that's going to imply we're looking to solve for time. We might have plugged in that T knowing that's what we have to solve for, but now we were a little stumped as to how we could play around, like, I don't know an A, I don't know a P, and so on. I'm just going to argue to you that you do. That for you to work through a problem like this, you can make your A and P almost whatever you want, as long as they have a relationship between the two. So for instance, I might even say, like, go ahead and pick a number. And maybe we go through and we say, like, okay, I'm going to pick a number. And I'm going to pick, like, something relatively ugly, let's say, or at least in terms of this case, like, that doesn't work out nice and neat. What if I said that my population is going to start with a value of 5? Like, I just picked 5. Okay, the question says, how long does it take to lose 90% of its population? So, for us to take a look at that, 90% of 5 is going to end up giving me 4.5. So that means in the purple, if I lose 90%, then I'm going to lose 4.5. That means I'm left with 0.5. Well, now you have starting value, you have an accumulated value, you see that your variable is up in the exponent, we should be good to solve that. So everybody's first action should be to divide out the 5. Well, if you take 0.5 and you divide it by 5, that would be the same as 5 over 50, or that would be the same as 1/2 over 5, 1/10. You can see we get the same thing. That your next line would be 1/10 equals 1/2 to the t over 18. Hopefully we're okay with that. Now, some people are going to look at that and they're going to say, like, really? You can just do that? Like, you can just pick numbers? And as I said, you can pick almost anything as long as they share that relationship. I might argue to you that there might be a more efficient route through. Like, couldn't we argue that every population starts with 100% of what it had? And so if I start with 100% and I lose 90%, then that leaves me with 10%. And so I could just plug in my 10 and my 100. And now when I divide out my 100, notice I get down to my 1/10, which was the same thing that I had before. Okay, there's actually even an easier way to think about it. That if you take a look at purple right now, you'll notice that I wrote down those numbers in percent form. The 10 and the 100 both represent percent. Well, what is 100% in standard form? Well, as a number, that's 1. What is 10% in standard form? Well, that just means like in a decimal. Well, then that would be 0.1. Now, I would have some people that would go through and they would now say, okay, I'm going to get rid of my multiply by 1, so I'm going to divide by 1. I might just say to you, like, why would you ever do that? Multiplying by 1 means I don't even need that. And there's your equation. That you may come in with that red equation to start off that problem. Nice. Okay, we can work our way through that problem relatively quickly. You take a look and you see where your exponent is. Where your variable is. It's up in the exponent. You got to get it out, which means we need to write both sides a power of the same base. Well, it's not going to be that easy to write 0.1 as a power base 1/2. And so what we've picked up in our skills then is if I can't write both sides as a power of the same base, then I know that I can take the log of both sides and I can then use my properties of logs to isolate for my variable. So by taking the log of both sides, that's what allows me to move that exponent out in front. Now all I have to do is just get my t all by itself. So hopefully we can see that we need to multiply out our 18 and divide out our log 1/2. So you give me that as an exact value for our log. Now we just have to turn that into a decimal. Okay, let's calculate it and round it off so we can talk about it the way we would talk about it. We're solving for a time. There is no inherent rounding rule in solving for time. So if you don't have a rule, then we're going to round off to 2 decimal places. So what I want you to do is to pause the video and work through your keying sequence to make sure that we can calculate that value. So we should be good to be able to go through, and hopefully we get down to 59.79, and we know how to define it. There's our hours. Okay, hopefully not too bad. What I want to do now is I just want to show you that there was a totally different way that we could have interpreted that problem and still been able to go through and solve. So I just want us to make sure that we're good in this context. Okay, we're going to put in an alternate solution. And I'm going to do that alternate solution in blue. Okay, so by no means am I saying that this is like a better solution. In fact, most of you are going to like the red setup. But I do want to talk about this alternate way to interpret the problem because it'll show us a little bit something extra in our mechanics, but it's also important for us to know like there isn't one way that we have to apply this relationship. Okay, instead, what I'm going to focus in on in the original problem isn't so much the half-life. But instead, what I'm going to do is I'm going to focus in on the 90%. Because when something changes based on percentages, then that's also exponential growth. I'm repeatedly multiplying by the same thing. So my focus now is going to be this 90%. Okay, this question says how long does it take to lose 90%? Well, then that means that the population is losing 90%. And if I lose 90%, then that means I have to be left over with 10%. That blue relationship always talks about what is left, what population exists, not what's gone. So what I could say then is my growth is 10%. Okay. The question asked me, how long does it take to do that? And how long does it take to G is by definition my period. Okay, well, what does the other information in the problem tell me? Well, it tells me that my half-life is 18 hours. So, if I start with 100%, then I have to get to 50%. I shouldn't have written in that. In 18 hours. I want you to see how that green statement is incorporated with that 50, 100, and now my exponent with the 18 on top. If I start with 100%, I have to get to half of that, and it tells me that my half-life is 18 hours. Now, what I'm going to do is I'm just going to clean that up again for everything that we just spoke about before, that really I have this. Okay, I'm going to solve that blue equation now. I'm going to do that in orange. So, my variable is up in the exponent. I got to get it out, which means I need a power equal to a power base the same. It is really hard to write 0.5 as an exponent or as a power base 0.1, so I'm going to take the log of both sides. By taking the log of both sides, that's what's going to allow me to bring that exponent out in front, attached by multiply. You might notice that something's a little different in this case now. That when I locate my variable, it's on the denominator here. So for me to solve for p, I have to get it off the denominator, which means I need to multiply it out. Now, I'm just going to put this line in green, because a lot of you are going to be able to skip that line. That is, we can see multiplying out the p, but then we notice that the p is not going to be isolated there because we're going to have a times log 0.5. And so at the same time then, we want to divide out that log 0.5, And so we get our P is 18 log 0.1 divided by log 0.5. And you guys can see that we're actually coming in on the same line. I just have log 1/2 written as a fraction versus log 0.5. The 1/2 has been converted to decimal. So I think it's important for us to be able to see that problem and that A, there's multiple ways to interpret it, but then B, well, what happens if we need to use logs to be able to solve? And to make sure that we're good to be able to isolate our variable wherever it is in our exponent. Okay, hopefully problem 3 was pretty easy to work our way through. Now I want to jump into something a little different. Okay, you take a look at problem 4, and I want you to give it a read. Okay, we're back. And so hopefully you read it and you started to go, okay, so now we're getting into some financial math. I want you to take a look at the relationship that I've put on the screen for you. Right off the bat, I just want you to notice this is the same relationship that we had and that we've been working with up to this point. It's A equals P times something all to an exponent. However, since in some of this financial math, certain concepts pop up all the time, that there can be some certain specific things that we could deal with, then some people really like to use that specific formula. So the only part that I want to break down then is the parts that are different. I want you to notice that our G has been changed into this 1 plus I. Okay, the reason for that, like if I was to tell you, let's forget about money, but that the population of a town was growing by 15%. Well, if you made your G 15% and then you multiply repeatedly by 0.15, I hope you can see that your population isn't growing at all, it's actually shrinking. Because your G is a value that's less than 1. That if you want your population to grow by 15%, then really what it is 100% of what the old population was, plus the additional 15% of growth. And so really what that becomes as decimals then is 1 plus 0.15. There's your 1.15. I think a lot of you guys would do that same sort of thing when you have to calculate like an after-tax price. Like if you're standing in the store and you're wondering, okay, how much is this going to cost for tax? You don't have to multiply by 0.13 and then add it on. I would hope that instead you would just multiply by 1.13 to get your total with tax. Same concept here. That if our investments are growing at a certain percentage rate, then maybe just to make it a little more explicit, rather than having to remember to do 1 plus for the growth, we can just put that straight into our formula. So you'll see that then up inside your brackets. That's why we have the 1 plus I for our G. Okay, now we've got the whole I thing. What that I represents is something called the adjusted interest rate. When you are quoted an interest rate, you are always quoted that interest rate per annum. And I'm hoping that with our experience last year, or maybe in some other courses, we're pretty good that per annum means per year. So you're quoted an annual interest rate. But it doesn't mean that that annual interest rate is paid annually. It doesn't mean that it's compounded annually. So what we have to do is we have to adjust the interest rate for how often we earn it. And what you'll see inside those purple brackets is how we can do that. You take the annual interest rate. An annual interest rate is generally represented by an R in a formula. And we just divide it by the number of compounds per year. How often are you going to earn that interest rate? Okay, we take a look up in the exponent, and our exponent can actually be simplified in this case, because really all we're trying to figure out is, over a period of time, how many compounds occur? How many times do you receive that interest? So, for anybody who goes, okay, I'm not very good with formulas or remembering formulas, then I might argue to you, just keep using your A equals P times G to the T over P and make the adjustments for this case. But for anybody that says, I'm okay to remember 2 formulas, then I would try to work to remember this one. I would argue for anybody that has the intention of going on to study business, especially anything that's financial or economic, then I would spend the time to remember that formula. You're going to see that probably in like an actuarial science course in the future. Okay, if we have that formula, then I just want to work our way through the problem to make sure that we're good with it. So, if you need to go through and deal with that problem, read it again, you should be good. Otherwise, we should be good to be able to plug in the parts. So, let's pause the video right now, give it a shot. Okay, we're back. I see that I've got a compound interest problem, and I might just write down that formula to help drill it in. I've been told that Peter invested $10,000, so he's going to put in an initial amount of $10,000. I then have my 1 plus. He's earning 6% per annum compounded quarterly. So even if I just blindly write that in then, there's my 6%. Compounded quarterly means 4 times per year. The question asks, what is the amount of the RSP after 5 years? And here's where we need to be good. I'm hoping that we have a 20 written down here. Off on the side, my number of compounds is going to be 4 times per year, the quarterly, and over 5 years, that's how I get my 20. Okay, you guys take a look at what you have in the red, and you can go ahead and turn that into a decimal right away. Same thing as I said earlier, I would just follow BEDMAS when I'm punching that into my calculator. If I were you, I would deal with my 0.06. I divide it by 4. Now what I'm going to do, since I found my adjusted interest rate, is I'm going to add on my 1. Now I have to put all of that to an exponent 20. Now let's multiply that by our principal or our initial amount. And since we don't have... since we are calculating money, then we're going to round that thing off to 2 decimal places, and we've got 13,468.55 as our calculation. So, hopefully that makes some sense in terms of our process, and we should be good to work our way through. Nice. Okay, let's jump into our next problem. Okay, you can pause that video right now and just give that problem a read. Okay, we're back. So, you take a peek at that problem, and maybe you go, okay, it looks like we're dealing with compound interest again, so I'm going to deal with my compound interest relationship. Okay, now what I want you to do, start off that problem, and all I want you to do is to go through your first 2 lines of your solution. So try to figure out how you can deal with that relationship. I want you to get to 2 lines and I want you to stop. Okay, give it a shot. Okay, we're back. So I'm hoping that we were pretty comfortable to be able to just go through and say, okay, Lois invested $5,000. She hopes that it's going to turn into $8,000. It's going to take 5 years to do that. The question asks me what rate of interest compounded monthly. So if 5 years are going to go by and I'm getting paid interest monthly, then 5 times my 12 gets me up to 60 compounds. That also tells me that I would be dealing with an annual interest rate of R, but 12 compounds per year. I think we did a great job if we were able to translate that problem into the red. So what I'm looking to do now is to solve for R. Now, I'll be honest with you, in terms of form, I wouldn't really care that much if you still had an I on top. I'm just going to argue to you, be careful. In the future, beyond this year, it may matter. Okay, we have that in that instance, and I'm going to argue that within 2 lines, I think we can really argue out how comfortable we are with our mechanics. Okay, the first thing. I take a look, I got to get rid of that 5,000, so I'm going to divide out my 5,000. Now, the nice part is if I divide out the 1,000, I see that I get 8/5. What I'm going to ask you to do is do not turn that into 1.6. The reason I say that is you can't always be guaranteed that when you divide out that initial amount, that 5,000, that you're always going to get a decimal that terminates. We need it to be exact. So I'm going to leave that as 8/5. That's a reduced fraction. I'm good. So we get to that point, and here's where I want to challenge maybe your thinking. That if our next action to solve that equation was, okay, so now I can take the log of both sides, then I'm going to argue we're struggling with our strategy. We have to stop for a second and remember that the question we always ask ourselves, where is our variable? And if I just highlighted my variable, there's my variable. And notice, it's in the base of a power. It's not up in the exponent. So I don't want to take a log at all. My job is to isolate that R. So, first action to go through and isolate that R, I have to get rid of that exponent 60. Well, how do you get rid of an exponent 60? Well, if we're stumped on that, then I might say to you, like, imagine it was an exponent 2. How do you get rid of an exponent 2? Well, we just take the square root. Well, how do you get rid of an exponent 3? Well, we take the cubed root. Well, how do you get rid of an exponent 60? We need to take the 60th root of 8/5. And if I do that, then my exponent is gone. I still have to get that R all by itself. Okay, so what's the next thing I can do then? Well, now I need to get rid of that +1. So I have to get my R term all by itself. Now, I just want you guys to watch how sloppy I start to write, because some of this could back to haunt us a little bit. Notice I'm already starting to write that out really sloppy. So say I go through and I go really, really fast. Okay, so the 60th root of 8/5 minus 1 is going to give me my R over 12. I just want you to look at that line and see how that could be confusing. So you take a look at it, and one of the questions that you might be asking is, okay, is that -1, supposed to be underneath the root or outside the root? The way I have it written, I don't know, like the subtraction is underneath, but the one... So I'm going to argue to you, really take your time when you are writing out any time you incorporate a root. So I need to have the 60th root of 8/5, and I'm going to subtract 1. Now I want you to see there should be no doubt that that -1 is on the outside of the root. Okay, to finish it off, to get that R all by itself, I need to go through and get rid of my divide by 12. So my R is going to be 12 times that big, ugly mess. And there we go. Now, what I'd like you to do is when you go through and you push buttons on that, and I need you to push buttons to make sure that we are good with our keying sequence. What I'd like you to do is round that value off, not part way. Notice I've done no rounding at all. I'm now getting to my final answer, so now is the time I can round. We want that to go to 4 decimal places. So I'd like you to pause it right now, work on your keying sequence, and we'll see if we match up when we get back. Okay, and we should be back. And if I go to 4 decimal places, that's what I get to. Now, you might be wondering, why are we going to 4 decimal places? The reason for it is quite often interest rates are rounded to 1 decimal place. So what I have sitting on the screen in red then is the decimal version of a percentage, something that's normally quoted as a percentage. So if I go through to change that now into a percentage, I'm going to multiply it by 100, then my interest rate is going to be 9.44%. By me looking at that to try to deal with my 4th decimal place, that's what's going to allow me to round my final answer correctly. So in this case, it was actually like 0.09436 something something. But because I see that that last 4 is small, then my final answer is going to actually be 9.4%. And there we go. Nice. Okay, I just want to kind of draw to our conclusion up to this point that we've been able to deal with a bunch of exponential growth and decay problems where you've had to build the equation. We've had cases where you had to solve that equation by just calculating an amount. We've had to go through and solve the equation by going through and trying to isolate a variable up in an exponent by either a power equal to a power base the same or taking the logs of both sides. We've now worked our way into some financial math where we just dealt with calculating an amount, or now we're actually solving for an interest rate. So we've dealt with a ton of mechanics after a bunch of setup. Where we're going to go next is we're going to introduce kind of a new topic. But what it's going to mean is we're going to deal with some functions, some growth and decay, where we have been given the equation to the function. Okay, let's take a look at the next problem. Okay, so I'd like everybody to just give question 6 a read. So I want you to pause it now. Okay, we're back. So the first thing that I want you to just kind of notice is that we have introduced a new concept to you, and it's that little power base E. Now, before anybody thinks that that is a variable in your equation, in your function, you should notice that our function is called P of t. That's telling you that t is the independent variable, so there's the variable in that function. So E does not represent a variable, and in fact, you may have noticed that over the years, we never used E to represent a variable. So I want to just make sure that we are good with the concept of E, and then we get to a point where we're functional in using it. The first thing I need you to know is that there's going to be a supplementary video in this topic. For anybody who really wants to see what E is, where it comes from, what does it represent, then I'm going to ask you to hop onto that supplementary video. For our purposes in this course, you are responsible for knowing what E is, but not necessarily all the detail to it. We will build on that as you move into calculus. So right now, what I would want everybody to do is to take out their calculator. We should have been using it throughout the lesson. And I want you to find what may be an, oops, that is a really ugly E. What may be an E on your calculator. Just make sure that it's not like an alpha key. Or likely you will have a button that shows e to the x. Now, for forwards, backwards calculator people, it's going to be important for you to figure out your keying sequence. For forwards calculator people, when you push that button, then it might automatically put in an exponent for you. And so you're going to have to be sure to enter in a 1 afterwards to put the exponent of 1 on E to get our approximate value. For backwards calculator people, you're likely going to have to push 1 and then your e to the x button to make sure that it doesn't interpret it as an exponent 0. If when you push your e to the x button, you get a value of 1 on your screen, then that's telling you you have a backwards calculator. It's making the assumption that you're trying to calculate e to the exponent 0. Okay, you find that keying sequence on your calculator, and we should be good to be able to get to some form of really ugly 2.7182818828 blah, 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 blah. Now, the biggest thing that I want you to get is I'm going to have some people that are going to look at this 18281828 and start to go, hey, there's a pattern, it repeats. Well, the next digit that comes after that is a 4. And so it doesn't repeat. And in fact, E is just an irrational number. It's a symbol that represents an idea. And it's a value that over time, people have been able to get to a closer and closer approximation of. It would fall directly in line with another irrational value that's represented by a symbol pi. So if you want to think of E as like pi, it's an irrational number. Pi, you can get along pretty good if you use an approximate of 3.14. Well, E, you can get along pretty good if you remember that it's like 2.71828. Most of the time for us, if we just remember that it's 2 point something, then that's going to be good enough for us, especially in this course. Okay, I would still recommend maybe that we don't hop onto that supplementary video, that maybe we leave that till the end. So if you are curious, which I love that curiosity, then maybe we just wait and we go through that discovery of what E is afterwards. What I'd like you to do is to hop in then, and if we know that E is just a constant, it's 2 point something, then we should be good to be able to treat it as such and go through and answer the 2 problems. So what I'd like you to do is I'd like you to pause the video right now and let's get a solution for A. Okay, pause it now. Okay, and we're back. So for me to answer problem A, it says estimate the population in 2040. Well, we've all read the problem. We notice that t equals 0 corresponds to the year 2000. So the actual value, t equals 0, would be like January 1st, 2000. So if I'm going to estimate the population in 2040, then really what I'm looking for is I'm looking for p at 40. I'm looking for 40 years after 2000. Okay, that means that I can make this substitution. I now have my e to the exponent. And I'm going to be honest with you, I don't even need you to calculate what 0.0087 times 40 is. We know that we're going to get an approximate right now. We can go ahead and calculate it. So let's go through and let's make sure that we've got a decent keying sequence to be able to calculate that. That means that we're going to have to use our E button on our calculator. And we should get some pretty decent practice to come in on approximately 48.15 million people. And there we go. Now, we don't need to put people on the end. It would be sufficient to say, my units would be millions, 48.15 million. And there we go. Okay, let's make sure that we're good on our keying sequence to get there. Okay, now I want us to work our way through B. Now, I'm just going to warn you, B's going to get a little ugly. It will. And I actually want to go through and maybe show a couple different ways to play around with B. But what I'd like you to do, pause the video now. Let's get a solution to B. Okay, we're back. So I'm going to take this solution maybe in its parts. So maybe we started off and we said, okay, well, the question says, when will the population reach 60 million? P of t is the population. And so I come in on this line, which is great. I think we should have been good on strategy. You see that your variable is up in the exponent. We got to get that out. So we're going to have to get that power all by itself. So let's divide out our 34. Now, if I divide out my 34, I'm going to get 60 over 34. that is a pretty easy fraction to reduce to lowest terms. And now we come in on something like that. The variable's still up in the exponent, so ideally I would like to get a power equal to a power base the same. However, probably writing 30/17 as a power based e might not be that natural for us. So we're going to take the log of both sides. By doing that, I can now bring my exponent out in front of my power, and now I can isolate and get my t all by itself. So I'm going to have log 30/17, and I'm going to need to divide out my 0.0087 and my log e. Okay, that is a pretty ugly expression, but that's also pretty simplified. Now, we would never talk that way. We're finding a year that doesn't make sense, so let's turn that into an approximate. What I'd like everybody to do, pause the video now, you go through and get an approximate for that value. Okay, and we should be back. And so we should get an approximate of 65.29. That's when we reach 60 million. Now, I do want to maybe talk to you a little bit about rounding, but we should be okay on that. And there's our, that is our solution to that equation. Now, the question says, when will the population reach that? And so therefore, we go through and we now have to put a year to it. So what I'd like you to do is just pause the video now and tell me in what year would we reach that 60 million? Okay, and we should be back. So I am hoping that we went through and we said that that would then be 2065 would be the year. Now, for anybody who was kind of looking at that and going like, well, duh, obviously it was 2065, I want to have a little conversation about how we can account for years. So what we're going to do is we're going to tackle this problem again. I'm just going to flip over onto a different screen. Okay, so what I'm going to do is just kind of shrink that down a little bit. And I want to make sure that we're okay with talking about our year. Now, where this can get a little difficult is the concept of time and us trying to put an ordinal number, like the first, the second, the third, or so on time. So I'm just going to jot down a couple things to make sure that we're good with how we talk about this. The first thing that I'd want to mention is if we got an answer of, let's say, like t equals like 0.1 or anywhere up to like 0.9, I hope that we can see that we have not completed one full year yet. And so that would still lead us to the year 2000. We're just at some span throughout that year. That if t then changed to like 1.1, like as soon as we cross 1, and anywhere up to like 1.9, we're going to be in 2001. And then the same thing, as soon as we cross 2, we would now be in 2002. And I just want you to notice that that's the same reasoning that we used in red to state that we would hit 60 million in 2065. We can tell from the decimal place, the 0.29, that we're going to hit it during 2065. Not at the beginning, but during that year. But it's still 2065. Now again, some of you are going to be going, okay, why is Gray spending so much time on this? It's because as soon as we start to talk about it with an ordinal number, we have to be careful. I want you to notice that if our time was anywhere from 0.1 to 0.9, yes, we're in the year 2000, but that's our first year. That as soon as we cross over 1 and we are now 1.1, well, then we've completed one full year. We're now a little bit into that next year. We're into the second year. And then the same thing, as soon as we have 2.1 up to 2.9, well, now we've completed 2 years. We are in our third year. And I just want you to notice that that can get a little confusing because all the numbers that started with 0 point something are in year 1. The numbers that started with 1 point something are in year 2, and so on and so on. That if we were to put that ordinal number on t in our red solution, you would tell me that it was during the 66th year. What that 65 means is we've completed 65 years. We are now into the 66th year. Okay, for anybody who finds that weird, just think about your age. And I always like to come back to asking you, when were you 0? And people often give you a weird look because nobody talks that way. That if you saw like a mother holding a baby and you asked, like, how old are they? Like, nobody says 0. That they're going to say, like, okay, well, they're 6 months, or they're 8 months, or they're 10 months. But that baby is living in its first year. So maybe we didn't realize it, like maybe we've never given any thought to it. But when you tell somebody your age, what you're actually doing is you're describing your completed years of life. That what that extra decimal represents is how far you are into the next year. So if you go to tell somebody that you're 17, you're actually living in your 18th year. Okay, just for us to be able to talk about it. Okay, what I'm going to do is I'm just going to get rid of all of the writing on that page, all of it, because I want to show you an alternate way to work through. Okay, what I want to do is I want to solve problem B again, but I want to deal with B in a different way. So we can pretty quickly get back down to that same point that we were at. Divide out. But rather than just generically say, hey, okay, I can't write 30/17 as a power-based E easily, so I'm going to take the log of both sides and generically take the log base 10 of both sides, we have another log that we can use. And it's a log that's programmed into your calculator. And it's a very specific log. That you have a ln button on your calculator. We would read that as ln. You might have thought that that was actually like a IN on your calculator, but no, it's really an LN. And what that represents is a log base E. So because I look at my blue equation and I see that I have a power base E, I might really like to take the ln of both sides. Now, for some people, you're going to look at it and you're going to go, no, I just want to keep taking my log. I'm fine with that. But I want to draw to your attention maybe the ugly keying sequence that you needed to go through to be able to answer the red form of your solution. And I want you to see how nice and neat this becomes if we use lns. Using a ln on the left side makes no difference. I could argue to you, hey, you get to write down 2 letters instead of 3. It's a little bit faster, but it really makes no difference. However, when I now have a single power inside my log, and I can use properties of logs to bring that exponent out in front, I am left with ln E afterwards. And if we understand that ln is log base E, then we should all be good to say that we understand that that equals 1. Right? E to what exponent gives me E? It's 1. And so I don't even have to write ln e afterwards because I would just be multiplying by 1. And so you'll just look at that equation and all you have to do is write down the blue. Okay, why does that make your life so much easier? Because now look at your keying sequence. I'm going to bet and say that some people had a pretty difficult time trying to figure out how to punch log e into their calculator. That some of your calculators define your log, but then when you also have to go through and punch in a power base e, especially if you have a backwards calculator, that you get to avoid all of that on your denominator. It's going to make your life so much easier. So my recommendation to you would be, if I'm solving an application question like this and I have to take the log of both sides, don't take it from base 10, take it from base e. Use lns instead. What I want you to do, just work your way through your keying sequence on your calculator. Like, crank that one out, see what we get to. Find your ln button. Take your 30 divided by 17. And now the nice part is you only have to divide by 0.0087. And you'll notice that we come in on the same thing. There we go. So we could finish off that problem by either saying 2065 or the 66th year. There we go. Okay, hopefully we're good with that, and we feel pretty comfortable now at least working with E. We'll get there as we spend some more time. Okay, we got one last problem to go through. So you take a look at problem 7. I want you to give that full problem a read. Pause it now. Okay, so we should be back. I think we take a look at that function and we go, wow, that function is relatively ugly given what we're dealing with. The only reason I wanted to talk about problem A, well, one of the reasons, is that just make sure that we don't do something silly. Notice in the problem, T has been defined in months. And so when you're asked to find what is the population, how many fish do you have after 1 year, we have to make sure that we subbed in 12. So for A, I am looking for a P of 12. Common mistake would be just to sub in your 1. So that's going to give us 20,000 over 1 plus 24 e to the exponent -3. Okay, now we need to go through, we need to come up with our keying sequence. We need to make sure we can punch that in. You get me an approximate number of fish. Okay, and so we should be back. And when we are, then we're going to get 9,112.08 fish. Now, what's really important for us is we can't round that yet unless we know what the population is doing. Remember our discussion on the very first problem. If the population was increasing, then we can never get 0.8 of a fish. Therefore, we have to round down. But if the population was decreasing, then we can't lose 0.92 of a fish, and so we'd have to round up. So the only way that I can round to the appropriate level of fish is if I know what the population is doing. Couple quick things. First off, look at your function and notice that you have an e function. That is a function that is based on your exponential. And it's only an exponential. There's no other type of function in there. So what that means is we know that exponential functions always increase or always decrease. They don't have a change of direction. And because of that, then I know that my population of fish has to always be increasing or always be decreasing. So if I just found out what the population of fish was at another point in time, then I would know what direction the population was going. For me, I think the easiest thing to do is let's just find out what's the starting population. I do that because subbing in 0 is nice and easy. It becomes this, of which I would hope that we wouldn't even write that down, that we recognize that e to the exponent 0 is going to give you 1. So it's 24 times 1. There's your 25. Well, let's take our 20,000 and divide it by 25. and we come in on 800 fish. And so as soon as I see in blue that I started with 800 fish in that lake, after 1 year, it's grown to 9,112 point blah, 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 blah. Well, then I know that my population is increasing, and therefore I know how to round my answer to A. I have to round down. There we go. Nice. Okay, I'd like us to take a look at problem B now. What is the maximum amount of fish in the lake? Okay. Now, some people could have a problem with that question right now. And it's given what I just said, like the maximum amount of fish. Well, we just found out that our population is increasing. Therefore, our population must always be increasing. How do we have a maximum amount? What we're going to do to take a look at that then is to look, well, if my population is increasing and it is always increasing, then really what I need to examine is I need to try to go forever into the future. And as soon as I write this down, some of you guys might have nightmares. And you might go, oh, wait a second. So now we're having to deal with limits again, like back in Unit 2? And I'm like, yes. However, I think what you're going to find is these tend to work out pretty nice. If I recognize that my population is always increasing, then I want to find out, what does the population tend towards? What is it approaching as we go forever into the future? Then I'm looking at the limit as t approaches infinity. Okay, why is this one not that bad? Well, what I'm going to recommend to you is don't imagine subbing in huge values for t quite yet. Because maybe we can see that I could rewrite that function in a better form. Notice what we have is our power. And all I'm talking about is our power. So if I just highlight that in green, the base of my power is e. So the negative exponent that I see only applies to the e, not the 24. So if I want to change that sign of the exponent to a positive exponent, then I need to move my power across its fraction line. Notice my 24 stays on top. It's not a part of the base. Okay, why does that make my life easier? Well, I just want you to think now about subbing in huge values for t into e to the exponent t over 4. If we allow t to become huge, and again, like what we talked about before, like 1 million, 1 billion, 1 trillion, and so on, like a trillion is relatively small, that divide by 4 almost becomes meaningless. That what we're really focusing in on is our e to the exponent t. Remember what e is. It's like 2 point something. So if you were going to put a huge number as an exponent on like 2, then e to the exponent t is going to grow or increase without bound. It's going to become huge. So now what I want to do is I want to look back inside my function, and now I want to zero in on my fraction. And notice we love fractions like that. We love fractions where the top is constant and the bottom becomes huge. Because we know that fractions where that occurs approach 0. Now we know that they don't equal 0 because the only way to equal 0 is if the top equals 0 and the top's 24. However, it's going to approach 0. So close to 0, you can treat it like it's 0. Well, then that means that my top is 20,000. My bottom becomes 1. And so we take a look at that and we go, oh, so my answer is 20,000. And this is where we have to be careful. The only way that I get 20,000 is if I took 20,000 and I divided by 1. The problem is that denominator isn't really 1. It's like 1 and a bit. And if it's 1 and a bit, then my answer shouldn't really be 20,000. It should be a little bit less than 20,000. Now, in the past, that hasn't mattered because we didn't have any inherent rounding rules. But now we do. I can't have parts of a fish. So I never get to the 20,000th fish. And instead, my population is going to be 19,999 fish. And there we go. Okay, the only thing that I want to finish off on is I actually wanted to show you what that function looks like as a graph. Because I think that if we tie those two ideas together, it's going to help you to get a concept of what was really going on with that function. Okay, so what you see on your screen is Desmos, and you'll look up in the top left corner. You'll notice that I've entered in the equation of that function. I've just replaced the p of t with y and my t with x, just to make it very generic. So when I punch in that function and you take a look on your screen, you might notice, hey, wait, we don't have a function here. I just want us to notice that our scales are horrible right now. Like my x-axis is negative 10 to 10. My y-axis is negative 10 to 10. That unless the maximum amount of fish we had was 10, then we can't see the function. So what I'm going to do is I'm going to adjust my scale. Now, you can use the zoom out feature clearly. On your phone, you're probably going through and using your fingers. However, I just want us to see that that starts to look pretty much like a vertical line. So what I'm going to do is I'm really just going to tweak each function. So within my graph settings, what I can do is I'm going to choose on my x-axis to just go from like negative 1 month. I'll even actually go negative 2 months, just so we can see a little to the left of the y-axis. And I'm going to go up to, let's say, I don't know, let's go like 5 years. So let's go 60 months. I might end up looking at that afterwards and going, ooh, I want to change that, but let's take a peek. On my y-axis, I'm going to go through and say, like, okay, let me have like maybe negative 100 fish so I can see a little bit below. You might be asking, like, why did you go negative 100? Like, well, maybe like negative 50 would be fine. But we just found that our maximum number of fish is going to be almost 20,000. So I want to make sure that I go maybe like 21,000 as my maximum number. That is 210,000. I do not want that. I like that. So just so I can see kind of on all sides of my axes. If we take a look at what you have on the graph, and I'm just going to shrink the whole graph down, just so we can make sure we can see the whole function on our screen. That what we now have is going to be our picture of our function. Now, if I went through and just tried to label some stuff on, then we should be okay down at the bottom to kind of look and say we were a little bit under 1,000. We found out that our starting population of fish in the lake were 800. We know that on 12 units, remember we're talking about each x value, t value being a month. So 12 units would put me right in about here. Then there is my 9,112 fish. And if we then start to take a look at what the trend in that graph does, you'll notice, if I just highlight here in purple, that as we get higher and higher, the population of your fish tends to level off. Now, from a science standpoint, that should make some sense. That in that lake, there's limited resources. Like you have oxygen in the water. You have food that the fish need. That if the population starts to get a little too big, well, then they're going to be fighting for resources, and the population won't be able to grow. Or in fact, in this case, the quantity of new fish that come into the lake that are born will match the ones that die. There's just limited resource. So if I just got rid of all those markings that we had on here, just because the graph's going to shift a little bit, then what I want to do is I just want to start moving, I want to start moving on Desmos. So what I'm going to do is just scale across, and even though I still have that little bit of highlight in there, let's not get distracted by that. But if I was to go and pick some point, then you can see that at like 59 months, we're almost at 20,000 fish. We're almost at 20,000 fish. Now, you can see my decimal points that Desmos allows me to round off to. We're up to 19,900.999. It's going to tell me that I hit 20,000. But you will notice we never go across 20,000. That what we actually have on that graph is our asymptote. We actually have an asymptote at y equals 20,000 that would represent that maximum value. The output value that our population approaches but doesn't quite touch. Okay, I'm just hoping that being able to see the picture of that function just gives us a little bit better understanding of what we worked with. Okay, today was a very, very big day. We covered a ton of review problems from last year, but because we now have the ability to solve some different exponential equations, we were then able to kind of take our applications and extend them. Hopefully we got pretty comfortable taking the log of both sides to solve, and when we have functions with e, we're good to just know that e is 2 point something, but that we also have the ability to take the ln of both sides to be able to solve. Okay, as I said, it was a ton of stuff thrown at you today. Hopefully it went well. Your job, jump in and get some practice with it. Okay, best of luck.